I will share a screen of what I would like us to do today. Okay. So basically, we continue to talk about grammars. We will talk about regular grammars. What I did during the lecture, I showed you how to convert automaton and how, if you are given a regular grammar, how do you draw the, how do you construct the grammar according to automaton structure. We also talked about how to simplify grammars. I was talking about simplification of regular grammar. Regular grammar, reminder, is a grammar where you have one variable at the left side, some word and additional variable or additional word, but you have a terminal symbols from the left before the variable in prefix. This grammar is called regular grammar. If we want a simplified regular grammar, then we should rewrite it in the following way. A will have some letter and then variable or another letter, but we have only one variable and one letter because the idea of simplified regular grammar is that you will draw later an automaton where A will be the state and variable B will be the state. You will transform from A to B with the letter sigma. And where you have a single letter, you will also perform the transformation to the new finite state. And you will draw this rule as automaton with two edges going out, one to B and one to final state. This grammar was regular grammar. I also talked about simplification of the context-free grammar. And to simplify context-free grammar, we need to eliminate, to remove unit rules and epsilon rules. We will practice it today. And we will also talk about Chomsky normal. All what I mentioned till now was technical stuff. One topic that actually demanded us to think a little bit about what we are doing and not to perform technical issues was closure of context-free languages. So I showed you some closures. I will do additional closure here during the lecture. We will solve several questions about proving or disproving that some grammar is context-free by using closure operations. And one of the closure operations was substitution. And it was relatively new for us because we didn't do it at all. So basically, we have a lot of things to practice. We will start with simple stuff. We are given several regular expressions. So we are talking about regular languages. And the topic is to write the grammar, regular grammar for each of the languages. So I ask you to start with language L1. Okay, thank you. I see that majority solved this question. So let's see the result. So basically we are talking about regular grammar. So we need to have an infinite number of zeros, but also an empty word is in our language. Therefore, S will derive 0S or epsilon. Okay, now language L2, I will give you a moment to think about the grammar. 0 or 1, but please pay attention. We're talking about positive closure plus. Therefore, currently an empty word does not belong to the language. Thank you. So let's continue. Okay. So basically, wait. I will provide 0s, 1s, but now to finish the derivation, I will use or 0 or 1 since empty word does not belong to the language. Okay, L3 is 0 star plus 1 star. So we are talking about 0 star or 1 star. So basically the idea is relatively simple, that we can use S to move or to 0 production rule or to 1 production rule. Okay, thank you. I see that majority finished. So I will give you a grammar, but yesterday someone told that this grammar is not regular one, and it is correct. So we will rewrite it to the regular grammar in a moment. Okay, so what I did, I produced zeros from variable A. Variable A actually produces a 0 star. B produces 1 star. And then from S, I moved O to A, O to B. But this rule is not a regular grammar rule. So I will rewrite the grammar. Someone proposed to write epsilon A, epsilon B. Epsilon is not a letter, so I can't write epsilon A, epsilon B. I will definitely produce epsilon from S. But then I will move with 0 to A and with 1 to B. So if I need to produce an empty word, I will produce it by myself. I will derive epsilon. If I need 1, 0, I will choose 0, A, and then A will produce epsilon. If I need 1 or 2 ones, I will move from S to 1B, then use 1B once again, and then use epsilon. Now, the rewritten grammar that we see here is a regular grammar. So please pay attention if you are asked to build a regular grammar. Regular grammar, the meaning is that you have some simplified regular grammar, that you have a letter and variable on the right-hand side of the production rule. Okay, the last language, L4.
Wait, can you explain again why the S is not regular grammar?
S, because according to the definition, S can provide all letter with additional variables. And I had S provides a variable without any letter, and S provides variable without any letter. This rule is okay for context-free grammar, but not okay for regular grammar. So I should not use single variable unit rules in a regular grammar. So what I did, I actually looked what I produced from A, and I saw that it was 0A, and I added 0A here, 1B here, and I also added epsilon from both of the rules that I had. But we will talk about, and I talked during the lecture about how to eliminate unit rules, because actually S derives A, S derives B was a unit rule, and you have a well-defined algorithm how to eliminate, how to remove all unit rules. Okay, last language, 0, 1 plus. So please pay attention once again that our minimal word is 0, 1, and then we have 0, 1, 0, 1, 0, 1 as many times as we like. So basically the structure of the grammar will be S derives 0, 1 S or 0, 1. Any questions? Good. So let's move to the next topic. This is with regular grammar. Okay. During the lecture, I talk about closure operation between context-free languages and sometimes context-free language and the regular language. So we know that context-free languages are closed under concatenation, under union. In regular language, what someone asked, multiple letter. A multiple letter, you mean in prefix? Yes. If you are not asked it in regular grammar, so okay, I would answer this question. Someone asked, is this grammar still regular? Yes, it's not simplified regular grammar, but it is a regular grammar. If I need to simplify it, I will write as provides 0a, and from A, I will derive the rest of the rule, 1s, and I will have 0b, and from B, I will derive a single 1.
Can't you do it from A as well? Just A, either 1S or 1, and save the letter.
Yeah,
No?
yeah, I can do it with the 1. Yeah.
Okay.
Here also 1, yes, it is the same rule.
Okay.
Usually when we rewrite according to the algorithm, they told if you have the right-hand side larger than 2 symbols, just add additional letter. So algorithm actually uses a lot of letters. Some can be reused, but usually according to machine algorithm, it will be a new letter, a new variable, without checking if we could simplify it. So what I did currently is machine algorithm, and you used your brain, and it was actually much better and much simpler grammar. Okay. So let's talk about closure of context-free languages. I showed during the lecture that context-free languages are closed under union, under concatenation. I also gave the definition of several additional closures. And I told that some of the closures we will prove during the practice exercise, and some you will prove or disprove during the homework. So the family of context-free languages is not closed under intersection. It is closed under intersection with regular language, but not closed if we are using context-free languages. To prove this theorem, I need actually to show an example where I have two context-free languages. I perform intersection operation, and the result of intersection operation should be not a context-free grammar, not a context-free language, but please pay attention that we still did not study which languages are not context-free languages, and we will study also the pumping lemma for context-free languages, but we will do it in 2 weeks' time. So basically, when I will prove this part, I will talk a little bit about non-context-free languages and how you can check that some language is not context-free without giving any proofs now. But later you will study how to prove that some language is not a context-free language. So basically, I would like to prove now that the family of context-free languages is not closed under intersection. I will choose two languages, L1 and L2, that will be context-free languages. I will define L3 as L1 some operation L2. In our case, the operation will be intersection. And I have to choose L1 and L2 wisely. So I will definitely have L3 as a non-context-free grammar. Okay, so let's talk a little bit about the idea of the proof.
Rina, what is not context-free language?
As I will start talking about it in a moment. For example, here, if I have infinite number of A's that I need to compare to infinite number of B's, but also to the same number of C's, I can't do it with a grammar. Because I definitely can produce the number of A's that equals to the number of B's. That's what I did here. That was actually the language L1. I have the number of A's equals to the number of B's. So here with the variable A, I produce for each A additional B. And then later I continue to variable C that produces any number of C's. So I actually can count till infinity with context-free grammar, but only for basically for two variables. I can compare between number of B's and C's. Once again, context-free languages, here is the grammar. From A, I produce the prefix of A's, doesn't matter how many A's. And then with variable B, I produce for each B additional C. So I definitely know that I have the number of B's that equals to the number of C's. But to compare A with B and with C, I can't do it with context-free grammar because I can only add A and B, but then I can't compare it to C. I can't add any additional C. So basically, for each set of variables here, or for each set of letters, I have to choose what I want to compare. Number of A's to the number of B's, number of B's to the number of C's, maybe number of A's to the number of C's, but I can't compare all the three because our model does not allow us. So I define an intersection of L1 and L2. The intersection of L1 and L2 is the language where the number of A equals to the number of B's, and the number of B's equals to the number of C's. So we are talking about A in power of n, B in power of n, C in power of n. And this language is not a context-free language. This was enough for me to prove that the family of context-free languages is not closed under intersection, since I found one case with two context-free languages. I showed what will be the language of intersection, and I know that this language is not context-free.
Why is
So
the amount? Why is the amount of C's and not M? Because they're both M in L1 and L2.
It doesn't matter. The idea is that it's the same number. You can use the additional letter K as a power. It doesn't matter.
No, okay, yeah, but I'm just saying, like, in L1 and L2, AB, and I understand why both AB, both of them are N, but the amount of C's in L1 is M. It's like different than
It
AB.
doesn't matter. It's any letter. But you know that intersection, because of the L1 part, You know that the number of A will be equal to the number of B.
Yeah.
You know, because of the L2, the number of B later will be equal to the number of C's. So basically, you need to show here the number of A's equals to the number of B's equals to the number of C's.
Okay.
So
Okay.
if you can't decide if to use N on OM, you can choose different letter. It doesn't matter. You just have to show that it's the same number. So it doesn't matter which letter you choose, it is okay. So basically now at the course, we only know that the language A in power of N, B in power of N, C is in power of N is not context-free language. So to prove that something is not context-free is basically for you currently to show in some way how you produce this language. Additional languages can be A in power of N, B in power of N, C, for example, in power of N plus 3. I can't produce it because after I decided what I compare, the number of A's to the numbers of B's, then I can't compare it with C's. If I produce the number of A and the number of C's that equals to the number of A's plus 3, it means that I already missed the B part. So I can't compare. I can't compare the length of 3 letters, of 3 terminal symbols. That's my problem with context-free language, with context-free grammar. And later, next week, we will talk about new model, push-down automaton, and we will understand why we can't compare the length of 3 terminal symbols. Okay. So, if you need to prove that some language or some closure operation is context-free, you need to show the grammar. How you combine given two context-free languages, how you combine them to get something that you want, the resulting set. Okay. So now we move to the clever part of this practice. We have several languages that were shown during the lecture. And we will prove that some languages are context-free and some languages are not context-free. And we have also some new operation that is not a regular operation. So we have a definition and we are asked once again to prove that this new language is context-free language. So basically, we will start with the first language, we will move to the second language and to the third. If you don't see the solution immediately, and in practice we have a limited time, it is okay. It is difficult questions. You need to think about them. So basically, I will give you several moments to think about the question, but I will later show my solution. Don't write it because I will publish the slides. Just listen and maybe ask the question regarding to the solution. So we have language L, A in power of N, B in power of N. We know that it is a context-free language. But now we have one limitation, that N should be different from 100. And we need to show that this language is context-free language. So I will use closure operation to show it, but I also wanted to show you that you could write the grammar for this language. I would like to produce all the words or all the words having the number of A equals to the number of B's till 100. A, B, A, B, B, A, 3 A's, 3 B's, and I will continue it until A in power of 99, B in power of 99. Then I will move to the following rule. A in power of 100, okay, S, B in power of 100. Actually, epsilon word belongs to the language, so I will add epsilon, and I will here 100 change to 101. But please pay attention that I use the simplified notation for writing. It is not a correct writing. If I would like to tell the grammar that I need a prefix of 101 A's, I need to write 101 A's. I can't write A in power of 101. It is not a correct grammar. It is a simplification just to show you that I actually could define a context-free grammar for this language.
Then how would I write it if I can do it?
Basically, it is a long writing. You will have to write 100 words here,
What?
and then 2 additional rules.
This is what you expect us to do in the homework?
No,
Oh,
definitely
just
not.
formally.
I would like you to use the closure operations, and I
Oh.
will do it in a moment. But just to show if someone in this specific question did not see the closure operation, you actually, in this case, could write the grammar. It was not so difficult or so complicated. I will definitely use the closure operation. So let's start the solution. I define a new language, LCAP, as A in power of 100, B in power of 100. This language is a finite language, therefore it's regular language. And now I will perform the following operation. I will define a new language, LCAP complement, as sigma star minus L cap. This language will be also a regular language, since sigma star is a language, a regular language. L cap is a regular language, and minus is a regular operation. The family of regular languages is closed under minus operation. And also I can use the idea that if L cap was regular, then L cap complement is also regular language. Why we showed it? We showed how to construct the automaton, so we know that this language is regular. Okay, let's start thinking what do we have in the language L cap complement. We have all the words in our alphabet, and we only deleted one word, A in power of 100, B in power of 100. We also have the words with infinite number of A's, with only B's, with B's before A's, A, B, A, B, A, B. Any languages are inside. The only word that is not inside is A in power of 100 and B in power of 100. Next operation, we will define a new language L two caps as the language A in power of n, B in power of n greater equal to 0. We showed during the lecture that this language is context-free language. You can produce A equals to the number of B's. And now we will perform an operation intersection between context-free language and regular language. And we had a claim, a theorem, that the family of context-free languages is closed to the intersection operation with a regular language. So according to the theorem that we did not prove, but it was given to us, we know that the resulting language, which is our language L, is a context-free language. Why the intersection between L two caps and L cap complement is our language? Once again, here we have all the words over alphabet AB, but we don't have A in power of 100, B in power of 100. Here we have all the words that have the following structure. Number of A's in prefix equals to the number of B in suffix. When we performed intersection operation, we have the language L with the following structure. Number of A's in prefix equals to the number of B's in suffix, and the only word A in power of 100, B in power of 100 is missing. So basically, we know that the resulting language is our language L. That's how I choose the first language, L cap. And now with closure operation, we know that this language is context-free language. That's what we were asked to prove. So you don't need to write a long grammar to prove that this language is a context-free language. Any questions?
Yeah, I have a question.
Mm-hmm.
What would have happened if we had a intersection between two regular languages? Not regular
It's regular
languages?
language. Intersection between two regular languages is a regular language. Each regular language automatically is context-free language because regular languages is a proper set of context-free languages.
Mm-hmm.
So if you manage to prove with all the closure operations that your resulting language is regular language, you definitely know that it is also context-free language.
And if it would have been a regular grammar?
Regular grammar is okay. It's once again, it's a regular language because from regular grammar you can build an FA. If you manage to build an FA, you know that is a regular language.
So what was it that you said that between two languages the intersection is not working?
Intersection between two context-free languages is not context-free language.
Okay.
Yes, that's what I did before. I choose context-free language with context-free language, and the result is not context-free language.
But if it's with the regular language, then it's fine.
Yes,
Okay.
yes.
Yeah, question.
Mm-hmm.
Removal. I mean, one language minus another. It's not closed.
No. Minus with between context-free languages is not a regular operation.
Thanks.
Okay. Additional language. Let's move. I will give you some time to think, but this proof will be not simple. We have a language L with all the words where the number of A's equals to the number of B's and equals to the number of C's. Without any limitations that A's have to be in prefix, B's in suffix, whatever. Any structure, any word W that has an equality between number of A's, B's, and C's belongs to this language. And we need to show that this language is not context-free language.
We can basically change it to a to the power of n, b to the power of n, c to the power of n. It's like the
No,
same.
but it's a subset because you have maybe A's in prefix, but also A's in suffix, B's and C's in between. It is not the language with the structure n power of 1 of n, b in power of n, and c in power of n, but you can go to this way maybe with closure operations and then shows that the resulting language is what you do. That's what I will actually do, but I will do it with a little bit different set of rules, because I will show you it in a moment why. So to prove that some language is not context-free language, the good idea is to assume that our language is a context-free language. That's what I did. And then to use a closure operation and to produce some new language that we should be context-free, and we will show that it is not a context-free language. That will be a good idea. So basically, like you mentioned, that's what I will do. I will start with the language L cap, which is A star, B star, C star. And this language is a regular language because we have here a regular expression. Someone yesterday asked me if it is a correct notation to write. Yes, please pay attention. We talked about language of regular expression, but that's what I wrote. So here you definitely write the language of the regular expression A star B in power of star C star. So yes, this definition is okay. This notation is okay. You can write it, you can do it. Okay, L cap is a regular language. And now what I will do is definitely what you mentioned. I will take L cap and I perform intersection with L. If L was a context-free grammar, we know that intersection between a regular language and a context-free language should be a context-free language. This one is a regular language. This one we assume that was a context-free language. So the result should be a context-free language according to the theorem that we were given. Okay, let's see what we have as a result. As a result, now I have the structure that I know that the number of A's that equals to the number of B's and that equals to the number of C's has the structure that A are at the prefix, B's are in the middle, and C's are in suffix. So the resulting language is A in power of n, B in power of n, C in power of n, that we know that is not a context-free language, but it should be a context-free language. So we have a contradiction, and the only thing that we assumed is the first claim of our proof. We assumed that L was a context-free language. Therefore, we know that our original language L was not a context-free language. Any questions? Good. Okay, the last question for today for us to think a little bit is the language L1, some operation which is called, I don't know how we should call it, diamond operation, let's call it, L diamond operation L2. You have a definition of this new language. It is X concatenation Y, where X comes from the language L1, Y comes from the language L2, and the length of prefix X equals to the length of the suffix Y. This is the definition of this diamond language. We need to prove that if L1 and L2 are regular languages, then this new language, L1 diamond operation L2, is a context-free language. So let's start talking a little bit about this proof, because this proof will be not so easy. I define a new language, L1 concatenation with DS sign and L2. And I call this new language L12. Please pay attention that now I have definitely a separation between prefix that comes from L1 and suffix that comes from L2. I have a DS sign somewhere, not basically in the middle, because for the language L1, L2, I don't need that the number of letters in L1 equals to the number of letters in L2. I don't have this constraint now. I'm talking about regular language. Why? L1 was a regular language, L2 was a regular language. The family of regular languages are closed under concatenation. The DS sign language is a finite language. It's also regular language. So I have a concatenation between three regular languages. The resulting language is a regular language. Okay, we move to the next step. We define additional language, L cap, as U DS sign V, where the length of U equals to the length of V. And we know that this language is a context-free language. We did it during last week recitation. But just to remind you, I can derive 0 as 0 or 0 as 1 or 1 as 0 or 1 as 1. So basically for each letter that I add in prefix, I add additional letter in suffix. And I can now in the middle derive a DS sign.
So you
So
assume L1 and L2 are built only of zeros and ones in this case.
yes, sorry, it was given. I think maybe I eliminated it. It was given that all three languages in this exercise are all over alphabet 01. Yes, we are talking about alphabet 01. Sorry, for language for all three claims in this exercise, the alphabet was the terminal symbols were zeros and ones.
But then the proofs are only hold for these kind of languages, right? If we use 3 characters, does it hold?
Yeah, your grammar will be much longer, but it's the same. I can use a simplified version of this rule. I will call it not D. Let's use
Sigma,
as a letter
yeah.
T, terminal.
Okay.
Terminal as terminal or DS sign. And terminal will derive, let's say that we have a 0, 1, 2,
Oh, okay.
3
And then,
letters, so not a problem at all.
okay.
This language is context-free because with context-free language, I can check that the number of letters in prefix equals to the number of letters in suffix. And here I have a definite definition where I have prefix, where I have suffix. I know that the prefix is before the DS sign, the suffix is after DS sign. So I know that I have a context-free language. Okay, now let's move to the next step. I will define the new language L2 caps as L1 concatenation with L1 L concatenation with L12. So I have once again intersection between context-free language and regular language. The intersection between context-free language and the regular language is a context-free language. So this new language is definitely a context-free language. The structure of the words in this new language is U comes from L1, V comes from L2, because it was the definition of L12, and the length of U equals to the length of V, and this comes from the definition of L cap. So we know that basically we are almost here. with only one problem, that we have a ds sign between x and y. We definitely have the words with the structure prefix comes from L1, suffix comes from L2. Between prefix and suffix, we have a ds sign, and the length of prefix equals to the length of suffix. So we are almost we moved to our language, but not yet. So here is the definition of our new language. Now I will use substitution. I talked during the lecture about substitution operation, where you use a sum function and you transform each letter O to a new set of letters, and this substitution called regular substitution, or you transform each letter to the new context-free language. And this substitution is called context-free substitution. In our case, I only want to remove the ds sign. So I will perform a regular substitution in the following way. I will define the function g, which for each letter of alphabet will produce the same letter. G of 0 will be 0, G of 1 will be 1, G of ds sign will be epsilon. This substitution is regular. Why? Because for each letter, I give a regular expression how to change it. So 0 is changed to 0, 1 changed to 1, ds sign changed to epsilon. Let's compute the language, the new language G of L2 caps. So the language will be a context-free language. Since the original language L2 caps was a context-free language, we know that the family of context-free languages is closed under substitution operation, or it is closed under regular substitution. It is also closed under context-free substitution. So the new language that I have is actually my original language, because I now from L cap, I actually remove L2 caps, I removed the ds sign. And if I remove the ds sign, I definitely have my original language. And I now managed to show that it is a context-free language. That's it, we finished this claim. Someone asked me yesterday, and I think that I usually get this question when I solve this exercise. Why we need a ds sign? Why we can't build L1 concatenation with L2? We can have a context-free grammar for UV if we produce S digit, where digit will be 0 or 1, and then with epsilon we move from this from recursion with S, and we finish. In this case, if I don't have a ds sign and I perform this intersection operation, I can claim that I have a word with a structure U concatenation V, where U comes from L1, V comes from L2, but I can't claim that the length of U equals to the length of V. Because, please pay attention, I can have an even length word, and all even length words actually can be divided to the prefix that equals to the length of suffix. So I now can't claim that U that is equals to V in length, that U comes from L1. I can have a structure that U will be an empty word, and it comes from L1. V is an even length word that comes from L2. And this combination will belong to the new language. because this combination, if we have an even length, then the resulting word can be divided to the prefix that equals in length in suffix. But now prefix does not come from the language L1, and suffix maybe does not come from the language L2. That is why I needed this DS sign as a separation between L1 and L2. And that is why later I needed the substitution operation to delete this DS sign. So once again, without the DS sign, the language L1 and L2 will be regular language. The language L cap, you can have a context-free grammar and it will be a context-free language. The language L2 caps will be a context-free language, but you can't claim that the language L2 caps is our language L1 diamond sign L2. Because it can be divided differently. You can't claim that the prefix U now comes from the language L1. It can come not only for the language L1, it can be, or it can have some letters from L2. So that is why I used the DS sign, and that is why this exercise I usually do with you in class, because it is not so simple to see. Someone needs to show it to you at least a first time, then you will know how to use it. Any questions? Good. So now once again we move. This was the only part of the practice exercise that actually we needed to think. The rest of the exercise is actually technical stuff. Okay, if we are talking about context-free grammar, and we will be asked to simplify it. Simplification means that we need to remove epsilon rules, and later we need to remove unit rules. Let's start talking about algorithm. How do we remove epsilon rules? So I'm giving a grammar, and I have here two epsilon rules, and I want to eliminate epsilon rule. To eliminate epsilon rules, the idea is, for example, I will start with A derives epsilon. So I need to find all the rules where A is used at the right-hand side, like here. And I will add additional rule without the A. So A will be replaced with epsilon. So I will rewrite this rule, A, variable B, and terminal C without A. Why? Because I replace A with epsilon. To remove B derives epsilon, I will do the same. I will find all the rules where B is used at the right-hand side, and I will replace each B with epsilon. And I will use all the combination of replacement. Please pay attention, I have two B's here. So I can, for example, at the first rule, I can replace one of the B's. And I can also replace two of the B's with epsilon sign. And then I also need to use this rule. In this rule, I also had B's. So I can rewrite it as A. One of the B's is epsilon, C. But I can also use that two of the B's will be epsilon. And now, after I checked all the possibilities for eliminating B and all the possibility of changing A to an empty word, now I have a grammar where a simplified version of the grammar. Wait, I will show you the result. And now can eliminate, actually delete what is derived from A and what is derived from B. But after I delete an epsilon rules, I don't know what is A and I don't know what is B. So I have this line, but A is does not exist anymore and B does not exist anymore. That is why I need to eliminate these rules because I don't have any definition for A or for B. So the remaining rule is only one rule, S derives AC. Let's check if it was our original language. How many words we could derive from this grammar? What is the cardinality of the language of this grammar?
2. AC.
2. AC. The cardinality is actually
Oh,
1 because you have one word, exactly. So this the language of this grammar, the language of this grammar G, okay, was only AC. So please pay attention that after removing epsilon rules, I also have S derives AC. So basically it's the same language. The question that is usually asked, how we managed to get here, I don't know. Maybe we had some automaton. Maybe this grammar was constructed with several constraints, that A was some kind of constraint and B was some kind of constraint. This original grammar that we were given is actually not a clever one, but that is a grammar that we were given. And if we are asked to eliminate epsilon rules, that's what we do.
Rina, question?
Mm-hmm.
The derivation you did, I mean, you took the entire word, then you took out B, and then you started taking out the...
I started with removing A derives epsilon. And then I have this rule A, B, B, C added. Then I started to eliminate B's. And then I have this one, and this one.
But after you removed A, why do you take into account the previous ones with A again?
Because I still did not eliminate it. If I eliminated it in, okay, what I did, I eliminated A derives epsilon at once, but I still did not delete A from the grammar. I know that I already did not have the definition for A, but I did not eliminate it. I eliminated it only at this stage. If I eliminated A previously, then wait, let's clear all drawings. Then the solution will be simpler. Then I will have S derives A, B, B, A, C, and then I add the rule without A. And then if I saw that A derives epsilon is the only rule and I deleted A, then I can eliminate this one and the next step will be much simpler. The next step will be to eliminate B derives epsilon. And once again, I have additional words and then I will delete B and all the right-hand side that has B. But actually, I will have the same one. Yes,
So,
your question was okay. So if you delete in steps, you could eliminate. I deleted both epsilon transaction in one step.
okay. So if I delete, I
And
first
you
add the
don't
word.
have any additional rules
No
from
recursive.
A. You can delete all the right-hand sides that has A.
So
So
wait.
if A derives epsilon is the only option, and we deleted A derives epsilon rule, we also deleted A from the language. So all the rules with variable a at the right-hand side can be eliminated.
So after we remove, okay, first we add all the rules with epsilon replaced with a, right?
With a,
To f
yes.
in this case.
This was
Then,
this one.
yeah. Then after we do that, we remove a, and then we remove all the states where a is shown because we replaced it.
Exactly. And then you can continue with B's. I did it in one step, so I had a longer possibilities, but the result is the same result. Okay, so the result after removing unreachable variables is, or undefined variables, is S derives AC. Okay. Additional technical stuff that we need to know how to eliminate the unit rules. The unit rule is some variable derives additional variable without any terminal symbols. So basically I'm jumping from one variable to another variable. And the idea will be that instead of writing A, we will replace here, instead of A, we will write the right-hand side of what is derivable from A. So let's do it in steps. Okay. Here I have two unit rules. S derives A and A derives B. And I will start with A derives B. Why I choose A derives B? Because I already see that here in B I don't have unit rules, so it will be a good idea to start. So how do I replace A derives B? Instead of B, I write all right-hand side of B's that I took from here. And I also add additional rules that I had for A derives B, so I keep it. So after part 1, I deleted the A derives B. Okay, now I continue. I still have a unit rule, S derives A. So I will do the same. I will replace A with the right-hand side of A, and I do it. And then I will also add additional B that I have, but I don't need the derivation of B twice. So if I have the same rule at the right-hand side, I write it only once. So I don't add additional B. I keep only the right-hand side of A's without any addition, since I don't have additional information. Now, the interesting question was, I actually finished with the algorithm of removing unit rules, but let's check if all variables are reachable. So please pay attention. I start with S. S at the right-hand side have B, so B can be reached. I look at B. B at the right-hand side uses only B. So basically I can see that A is unreachable and I can eliminate it. If I can't derive A when I start my building parsing tree from S, from the root S, and if A is never reached, and here A is not at the right-hand side of anything, so it can't be reached anymore, so I can eliminate A. Any questions? So basically, the result will be, so the elimination algorithm finishes here, but the next step, if I continue with the simplification of the grammar, will be to delete this rule, since we don't need it anymore, since variable A is unreachable. Okay. The last question for today. At the end of the lecture, I talked about Chomsky normal form of the grammar. And the idea of Chomsky normal form, that for each variable, we have or derivation of the single letter or derivation of two variables. We can simplify or rewrite any context-free grammar to Chomsky normal form grammar. We need to eliminate epsilon rules and unit rules at the beginning, and then we will continue with rewriting it, each rule to having only two variables. I will do it in a few moments' time. And the idea of Chomsky normal form that if you are giving a word of the length n, then you know that in 2n minus 1 steps, you will derive it according to the grammar written in Chomsky normal form. Chomsky normal form is also very comfortable for programming because we are talking about binary parsing tree. We will have only two children, and in a lot of programming languages, we have binary tree as a class or as a data structure inside the language. It is predefined, and any other tree we will have to write by ourselves. So sometimes it is comfortable to rewrite the grammar to Chomsky normal form and then use predefined classes or structures in programming language if I need to write some checker for context-free grammar. And if I would like to know if the language belongs to, if the word belongs to the language, it will be comfortable for me to rewrite the language in Chomsky normal form, to write a program that checks it, and that's it. So we will solve this question in several steps. We are given the grammar and we are asked to rewrite it in Chomsky normal form. So basically the idea is that for Chomsky, we have to start with adding a new variable s cap that derives s. If the empty word belongs to the language, here, only here, we allowed to add an empty word. And later, we will have our original grammar rules. So here will be our grammar as derives whatever. And then we will continue. Eliminate epsilon rules, eliminate unit rules, rewrite the grammar in the form that at the right-hand side, I will have only or single letter or two variables. That's it. That's what is I am allowed to do. To rewrite means that I will add additional variables. I can't solve this question without adding additional variables. Okay. So let's start our solution. Okay. We will remove epsilon rules. I'm giving you a few moments. Please remove epsilon rule. We have one epsilon rule. A derives epsilon. Please remove it. Just to check. Okay. Thank you. Okay, I see that everyone finished. Very good. Thank you. So, after removing epsilon rule, A was written only in one rule at the right-hand side. So basically, I add S cap derives S as I was asked at the first step of the algorithm. I add S derives 0 since I replaced A with epsilon. So I added 0. and I still have A derives epsilon, but it will be deleted at the next step. So now when I edit 0, I can delete this epsilon. Okay, the next step will be remove unit rules. Please pay attention that we had a unit rule here, and now we edit additional unit rules when we additional unit rule when we move to the Chomsky normal form. So please remove both unit rules. I'm giving you some time to solve it by yourself, and then I will solve it together with you. Okay, 2 students finished, 3. Okay, everyone finished. Thank you. Okay, and polling. So we will move to the next step. I replace S, B derives S, so I write what is derivable from S. Please pay attention that I had 0 and I also added 0. I don't write B derives 0 twice. I write it only once. Then I replace the unit rule. Wait, I'm moving at the wrong direction. S cap derives S. So basically I replace, I write here the right hand side. Now I should check that all variables are reachable. So let's start. From S cap I can reach A and B. So A and B already reachable. And from A I can reach S. So I can't eliminate anything. All the variables are reachable in this grammar. So I can't simplify it anymore. So now we have a simplified form of the grammar. We don't have unit rules and we don't have epsilon rules. So now we move to the next step of Chomsky normal form, and we need to rewrite the grammar in the following way. That at the right hand side we will have only or single letter or only variables. So please pay attention. I took all the rules where I don't have only single letter at the right hand side, and I'm rewriting the rules only with variable. So I had the rule S cap derives A0. Now I rewrite it as A S0 new variable, where from S0 I derive a 0 sign. I had the rule 0B0, so now I replace it with S0BS0. The single letter, the single terminal symbol is okay. And I do it for all the rules. Okay. The next step. I need to find all the right-hand side rules which have more than 2 variables. I need to find all the rules where I have at least 3 variables. I can have more. And I need to rewrite those rules with having only 2 variables. So how can I do it? I can write A derives B and some additional variable X. X will derive C and the rest of the rule, let's call it Y. Y now will derive what is left here, which is BD. So infinite number of steps, I can rewrite the right-hand side of any rule to having only 2 variables. Okay, so let's continue with our rules. The only rules that we have three variables at the right hand side was the rules S cap derives as 0, B as 0, and we had the same rule derived from S and from B. So I will rewrite those rules. S cap will derive S0 and the new variable C, where from new variable C I will derive the rest of the rule, which will be B as 0. And actually I will use it 3 times since I had the same right hand side 3 times. And what we have now is the grammar rewritten to Chomsky normal form. That's it. We finished the algorithm. Any questions? If not, thank you very much. We finished for today. So basically in your next homework, you will have several questions. Some questions will be technical questions. Given on automaton, write regular grammar. Given regular grammar, write an automaton. Given a grammar, simplify it, rewrite it into Chomsky normal form. And you will have 2 questions where you actually have to think a little bit about. You will have to prove some theorems about closures of context-free languages, and you will have to prove or disprove that some languages are context-free languages using closure operations. So, once again, part of the homework is actually technical, very boring, but we need to practice it. And the part of the homework is actually something that you need to think about. Any questions? Because I finished. So if you have questions, I will be glad to ask. If not, we finished for today.
Thank you, Ina.
Thank you.
Thank you. Have a nice day.
You